Professor Robert Taylor wanted to show me an experiment that opens a door on what happens at some of the coldest extremes of temperature physically possible.
So that's the nitrogen going in.
Wow, you've got to be the stupidest man I've ever met in my life. That's not liquid nitrogen, that's superfluid helium.
Wow!
Let me drop some speed facts on you, Ben, because I got a feeling we're in some grade 12 kid's physics class and he's got an arbitrary time limit he has to meet. This superfluid stuff has some wacko properties. It's defined by something called a two-fluid model, where past a lambda point, a sample is composed of a ratio of a fluid component and a normal fluid component, which sum to a total density. The total density remains constant, but this ratio of superfluid to normal fluid increases as the sample reaches the big 0 Kelvin. I mean, overall, these superfluids have some crazy properties. Due to all the atoms sharing the same quantum state, they can be transferred without energy, tend to boil without bubbles, and can't be trapped. Fluids tend to climb the walls of their container, but a conventional fluid like water only climbs to a certain extent, seen by a meniscus in a test tube. This is because friction, or viscosity, prevent the fluid from going any higher. But whoa, here comes a superfluid with 0 viscosity. Due to its shared quantum state, it's climbing right over the top. Zoo-wee mama. Oh my. Don't look now, but the fluid is now pouring straight out of the bottom of the container. This could only be explainable by its shared quantum state once again. All of the atoms have the same momentum. If one moves, they all move. Great Scott, is that a fountain? Oh mama. It can only be explainable by somebody using photons to excite superfluid, likely performed by running electricity through a wire submerged in the fluid, in which doing so would form a fountain vertically upward off the surface of the superfluid. I can only imagine the height of the fountain can be adjusted by changing the voltage of the wire. No way! These bad boys also have high thermal conductivity. Conventionally, when heat is added to a system, it slowly diffuses throughout. In contrast with the superfluid, heat is transmitted through a phenomenon known as second sound. This is a quantum mechanical phenomenon in which heat transfer occurs so fast it is like a wave-like motion, instead of the common mechanism of diffusion. Whoa, 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 watch out, Ben. That's a vortex. Oh my god, I mean vortices. And they're quantized. Those are no ordinary whirling mass of rotary motion in a liquid or gas. In contrast to regular vortices, quantized ones can only move at certain values, while in regular fluid, the strength of the vortex is uniform to the rotation of its container. A superfluid will remain perfectly still, even if its container is rotated, unless the rotation reaches a critical speed. Thus, since superfluids rotate in quantized vortices, the rotation is not uniform.
That is mind-blowing, isn't it?
Ben, please just stop talking.